Today we will talk about the min-max theorem and Lagrange multiplier, and we will compute curl divergence and Laplacian. Okay, the first thing is the min-max theorem. If our function f is continuous, where closed bounded domain D, then we can say that f has global min-max on D. To solve and to find the min-max, minimum or maximum, we want to find the critical point in D, and also we want to check the value on the boundary. So let's solve the problem using the theorem. Actually, when you see this problem, you can see that this f is continuous, and we can take a derivative of f because it's just a polynomial function. Okay, so first of all, we can say that since f is polynomial, it is very good function. F is polynomial. So it is continuous on our domain D. Actually, as you can see, this D is closed and bounded, right? It looks like if it is the Cartesian coordinates, then x is from 0 to 3 and y is 0 to 2. So our domain D is like this yellow rectangle here. It is closed and bounded, right? So we know that f is continuous on the closed and on the closed bounded rectangle. So by our min-max theorem, we know that there is the existence of global maximum and minimum. Or you can say that the absolute maximum and absolute minimum, like that. Global maximum and global minimum. Indeed. Okay, so by using the theorem, we can say that the existence of the global maximum and minimum on D. So we needed to find the maximum and minimum by solving, by finding the critical point. So our step one is find the critical point. It means that we want to find the points such that gradient f is equal to 0. Right, so find the gradient f. It is just the fx and fy. So if you take a partial derivative, then you get 2x minus 2y. And here you get 2 minus 2x plus 2, right? So we want to find the point such that this gradient f is equal to 0. So it means that we have two equations like 2x minus 2y equal to 0 and minus 2x plus 2 equal to 0. From the second equality, we have x equal to 1 here. And if you put x equal to 1 in the first equation, you get y equal to 1. Okay, so our critical point is 1, 1. And since we are interested in maximum and minimum values, so let's compute f1 comma 1, then you just get 1 minus 2 plus 2 is 1. Okay, this is the first step. The second step is check the boundary point. So first step is critical points. The second step is check the boundary points. So as you can see, there are 4 boundaries, 1, 2, 3, 4, right? So let's say that the L1, L2, L3, L4. It is each side. It is L1 and it is L2 and it is L3 and it is L4. Okay, then we can say that on L1, if you think about the point x comma y on L1, then y must be 0 and x must be from 0 to 3, right? So on L1, you can say that y equal to 0 and x must be from 0 to 3. So our function f of x comma y is actually y is 0, right? So fx comma 0, I put 0 here because our y is 0. Then we get, if we put y equal to 0 here, then it must be x squared, right? So you know, it is just the one variable function. It is just the f of x equal to x squared, and our domain is from 0 to 3. Okay, so as you can see, x squared is like this. And if we think about the 0 to 3, then minimum is obtained from at 0 and maximum will be obtained at x equal to 3. Okay, so we can say that since this function x squared is an increasing function, so on L1, minimum is obtained at 0, x equal to 0, y must be 0. So f of 0 comma 0 must be 0, and maximum will be obtained at x equal to 3, and we know that y must be 0. So it is the 3 comma 0. And if you put 3 and 0, x equal to 3 and y equal to 0, then it must be 9. Okay. So on L1, we compute this one. And on L2, you can see that on L2 is here. Then if you think about the point x comma y on the line L2, then x must be 3. And y must be from 0 to 2, right? 0 to 2. So on L2, we have a condition that x must be 3 and y must be 0 to 2. So the point f of x comma y on L2 must be f of, 3 comma y, because x is fixed by a number 3. So we just put 3 comma y here. So if you put 3 here, then you get, it is just the 9 minus 6y plus 2y. So it is minus 4y plus 9. Okay, then it is the decreasing function, right? So decreasing function, so maximum must be at 0, y equal to 0, and minimum must be obtained at y equal to 2, right? And x must be 3 here. Because on R2, x must be 3, so it must be 3. So if you compute the value of 3, 0, it means that if you put y equal to 0 here, then you get 9. Okay, you get 9. And here it is 3, 2. So if you put y equal to 2 here, then you get negative 8 plus 9, it would be 1. Okay, you need to check these points because these points are the, we need to compare the values of these points. Also these critical points here. Among these points, the maximum value is the global maximum. But we need to compute more things because we need to compute L3 and L4. On L3, I will copy and paste over this graph here. Just a minute. Okay, so on L3, x is no, y is fixed. On L3, y is 2, and x is from 0 to 3, right? So we can think about the x comma 2. It'll be our function is here. Okay, so it'll be x squared minus 4x plus 4. I put y equal to 2 here. So we get the equation like this. And as you know, it is the quadratic equation. So you get this one. So it means that if x equals to 2, then this one must be 0. And it'll be like this graph. Okay, so it is 0 and 3. Actually, f of 0 is the maximum and f of 3 is not maximum. Okay, f of 0 is maximum and f of 2 is minimum in this graph. So our maximum must be at x equal to 0. The reason why I've x equal to 0 is a maximum is, as you know, this function is like that 1, 2, 3 here, and it is symmetric with respect to the line here, x equals 2. So f of 3 is equal to f of 1, and f of 0 must be higher number here. So since our x is from 0 to 3, like a 0 to 3, so this point must be the highest value of this graph. So maximum value is obtained at x equals to 0. And our y was 2. So we want to calculate the f of 0, 2. And if you put 0 here, you get 4. Okay. And minimum is obtained at x equals 2. And y must be 2, so it must be get 0. So if you put x equals 2, then you get x equals 0. Okay, so let's check these values. And last one, we will think about the L4. Okay, so in L4, you can see that the x must be 0 and y is from 0 to 2. So x equal to 0, y is from 0 to 2. So you can say that f of 0 comma y is the function, like if you put x equal to 0 in our given function, then you just get 2y. It is 2y, okay? So, this is the increasing function. So minimum is obtained at 0 and maximum is obtained at 2. So maximum is attained at y equals 2, and minimum is obtained at x, y equal to 0. Our x must be, 0. So in this case, f of 0, 2 is 4, and f of 0, 0 must be 0. Okay. So our candidates are, first thing, this is from our critical point, f1, 1 is 1. And we get f of 0, 0. We get this one on L1, and on L2, we get this one, and L3, we get this one, and lastly, on L4, oh, there must be 4 and 0. Okay, among these points, you can see that 9 is the maximum value. So you can see that these are the same point. So our maximum is obtained at 3, 0. Obtained at 3, 0, and its value is 9. And our absolute minimum, our global minimum, is, as you can see, it is 0, 0, and there are 2 points, 0, 0, and 2, 2. So minimum is obtained as 0, 0, and 2, 2. And these values are 0. Okay, so our maximum and minimum on our rectangle D. So by summary, when you want to find the absolute maximum and minimum on the bounded and closed interval, or closed rectangle or region, then first thing we want to do, is, let's say here, what you want to do is check the continuity on the domain, so we can apply the theorem, min-max theorem. So we know the existence of maximum and minimum value, and then you need to check that you need to check the critical points. After you find the critical points, get the values of the point, something like that. And the third one is thinking about the boundary points on the boundary. Find the maximum and minimum on the boundary. As we saw in the before, like on L4, on L3, like that, like this. At the boundary, on the boundary, we found the maximum and minimum as cases. So find the maximum and minimum, and these are our candidates. So among these numbers, compare the numbers. So like this, we collect all numbers, these numbers, they are candidates, and we want to pick the maximum value among these numbers and minimum numbers among these numbers. So among these numbers, minimum of these numbers must be global minimum, and also for the maximum. Okay, so first thing, you want to check the continuity and find the critical points and the values at the critical points, and find the maximum and minimum on the boundary, and then compare these numbers, and the highest number is the global minimum, global maximum, and the lowest number is the global minimum. Okay, it is the steps. But as you can see, when you think about the boundary case, if our domain looks like ugly, then it'll be hard to find the maximum and minimum. So there would be one case we can apply Lagrange multiplier. Okay, we will think about this case later, but maybe it would be your homework problem. In your homework problem, maybe there a bit is set like d equal to something like x comma y, and x squared plus y squared is less than or equal to 1. As you can, in this case, if you draw region D, then it must be like this. Radius 1, this one. It is closed and bounded region. But you know, the first thing is to find the critical points, okay? And the second thing is the boundary. Think about the boundary. It means that the boundary is just the circle, right? Circle. So it is x squared plus y squared equal to 1. So in this case, we cannot guarantee that we can find the maximum and minimum using this method on L3, L4 like that. It'll be hard to find the maximum or minimum, or maybe it can be, but there is another method, which is the Lagrange multiplier. I mean, because this x squared plus y squared 1 is our constraint, so we can use the Lagrange multiplier. Okay, let me see. So f and g is the function on some domain. And if f has a local min-max object to the constraint, g equal to k, g equal to constant, and then gradient g equal to 0 or gradient f equal to lambda times gradient g. Okay, so we will apply this Lagrange multiplier method to find the min-max problem. So in this problem 2, let's find the points on the sphere x squared plus y squared plus z squared equal to 4 that are closest to and the farthest from the point. Okay, so what you want to do is the closed and the farthest. So we need to think about the distance of 2 points. So let's say that the distance between some point x comma y comma z, it is the point on the sphere, okay? And this point in 3 comma 1 comma minus 1 is given by, as you know, the distance is given by x minus 3 square, y minus 1 square, plus g plus 1 square. Okay, x minus 3 square, y z, like that. We can calculate it like this. So we can say it is the function of f of x comma y comma z, but if there is the square root, it is hard to take a partial derivative. So as you can see, if this one is smaller, then the square root of this one must be smaller. So it is the same thing as the think about the square. If it is the d, it is just the polynomial. Okay. So if we want to the points that they attain a maximum or they attain a minimum, then it is the same thing that finding a points that D square is minimum or maximum. Okay. So let's say that it'll be f of x comma y comma z for our convenience. Okay. And as you know, this x comma y comma z is the sphere, so it must be satisfied this equality. So let's say that g of x comma y comma z is equal to x squared plus y squared plus z squared, and it must be 4. Actually, it is our constraint. So yeah, according to the method of a Lagrange multiplier, we solve gradient f is equal to lambda of the gradient g. Before this, we want to find the gradient f and gradient g. So in this case, we find gradient f is like a 2x minus 3 and 2y minus 1, comma 2z plus 1, okay? And here we can find that g, gradient g is just the 2x, 2y, 2z, right? So gradient g can be 0 at x equal to 0, y equal to 0, and z equal to 0. But as you can see, this point is not on the sphere. So we can say that gradient g cannot be 0 on our sphere, on our constraint. Okay, so we can say that by the Lagrange multiplier method, gradient f equal to lambda of lambda times gradient g, satisfied at the local maximum and minimum. Okay, so we want to solve this equality. We can say that it is 2x minus 3 to y minus 1. Sorry. 2z plus 1 must be equal to 2x, 2y, 2z. So we get the equation x minus 3 is equal to lambda. Sorry, I must be multiplied by lambda here. So it must be lambda x, and y minus 1 is lambda y. Z plus 1 is lambda z. I just divided by 2 on the left and right hand side. So we get this system of equations. And we have the constraint x squared plus y squared plus z squared equal to 4. Okay. So let me see. To solve this equation, what you want to do is, let's think about this one. You know, it is x minus lambda x equal to 3. So we can say that it is 1 minus lambda times x equal to 3. So if lambda is not 1, it means that if 1 minus lambda is not 1, not 0, then we can divide it by 1 minus lambda. So x must be 3 over 1 minus lambda. Okay. Then how about the case lambda equal to 1? If lambda equal to 1 here, as you can see, this equation must be x minus 3 equal to x. But it is impossible because it must be minus 3 equal to 0. It is impossible. So actually, lambda must be not 1, okay? Because if we put 1 here, then x minus 3 equal to x is impossible equation. So lambda must be not 1. So we can divide it by 1 minus the lambda here. So x must be like that. And in the same method, we can see that it is y minus lambda y equal to 1. So we get 1 minus lambda times y equal to 1. So since lambda is not 1, we can divide it by 1 minus lambda. So we have 1 minus. Something like that. Let's do it the similar thing here. Then we get like this. And as you can see, z is minus 1 over 1 minus lambda. And since we have three things and we just put these ones in the last equation, then you can get x squared means 9 over 1 minus lambda squared, okay? Y squared plus z squared. Then it'll be 4, okay? I just put x equal to this one in the here, y equal to this one in the here, z equal to this one in the here. Okay, so I have this equation and you can calculate it like 11 1 minus lambda squared equal to 4. So it is 1 minus lambda squared would be, it'll be 11 over 4. Okay. So 1 minus lambda is plus minus root 11 over 4. It is equal to root 11 over 2. So our lambda must be 1 minus, actually plus minus. Yes, lambda must be this one. Okay, so if you find the lambda, then you can get x here. Okay, to find this one, actually, we need just the, 1 minus lambda here. We can put 1 minus lambda there. Then we have x equal to, just a minute, if 1 minus lambda is plus root 11 over 2, then you can see that x must be 3 over, it is root 11 over 2. So it'll be 6 over root 11. And y must be, 1 over root 11 over 2. So it'll be 2 over root 11. And z must be negative 1 over root 11 over 2. So minus 2 over root 11. Okay? So they are 1 point. And there is another thing, minus here. So if you put the minus root 11 over 2, then you can see that it'll be negative 6 root 11, and y must be minus 2 over root 11, and z must be plus 2 over root 11. Okay, so by solving this equation, we get 2 points. So yes, actually what you want to do is trying to find the closest and farthest point. Okay, so if you put these values here, then you can verify that which points are the closest point. But after this, okay. Actually, I don't want to calculate this. Yes. Must I calculate it? It's very looks not good. These numbers. Maybe it is better to use calculator. Okay. After using calculator, you can see that this is the closest point. I mean, we need to, our f is this one. So after put f of 6 over root 11, 2 over root 11 minus this one, calculate this one. And for this point, calculate f of minus 6 over root 11 minus 2 over root 11 and 2 over root 11. Calculate these points and compare it. So if you calculate it, then it must be like this. Okay, so this is the minimum value of f, and this is the maximum value of f. So our closed point must be 6 over root 11, 2 over root 11 minus 2 over root 11. And the farthest point must be minus 6 over root 11 minus 2 over root 11 and 2 over root 11, like that. Okay. So in geometric meaning, there are the XYZ here. And our sphere must be like this one. It'll be for, no, 2. Okay, there's 2. It is this sphere, like this one. And our 3, 1, minus 1 must be the point like that. Then, this point is the closest point. And after it, just a minute. I think it is better to use the like that. Yes. After passing through the sphere, there must be the point here. This point is on the sphere, and it is the farthest point. Okay, this is just the geometric meaning of this problem. Find the points on the sphere, so these points must be on the sphere, and we want to find the smallest distance and the maximum distance from this point. So if we take this point, then it'll be the distance of the points. So this point must be the closest point, and after passing through these points, here is the farthest point. Okay, we find these points using the Lagrange multiplier. Okay, now let's calculate the divergence curve in Laplacian. So if our vector valued function is represented like this one, we can calculate divergence like just the sum of the partial derivatives. I think it is better to see this definition by solving, by calculating a divergence. So let's copy and paste it on the problem. From this one, if we set it, it is just the xz comma xyz comma minus y square. Okay, so here the fi means just the first, second, third coordinates. So when you want to do calculated divergence, actually it is given by f. So divergence f is summation of the functions, but I think it is just the 3 coordinates, so I will just write all things. df1 dx, because x is our first coordinate, and df2 dy plus df3 dz. maybe someone can be confused because we sometimes use this notation for the first partial differentiation like fx. But as you can see in this setting, we just put the first coordinate as the f1. So it is just the coordinate function xz, and dy, the second coordinate xyz, and the third coordinate, minus y squared. Then you can see that it is just the z plus xz plus 0. So divergence f is z plus xz, okay? So you can calculate the divergence like that. And if we want to calculate a curve, you know, curve is defined like using a, oh, why I cannot, just, why? Oh my God, just a minute. What product? I forgot the notation of that one, but yes, we can calculate it using the determinant of this one. Not with product. With product, I mean, okay, it's okay. Okay, to find the curve of f, we needed to calculate this determinant. In this case, for this our function f, from function f in our setting, it must be I, j, k, ddx, ddy, ddz, and f1 here is just the first coordinate function, so it'll be xz, and second coordinate function, and the third coordinate function like that. Okay, and it'll be the I, dy, ddz, xyz minus y squared, negative j, it'll be ddx, ddz, and xz minus y squared, plus k, ddx, ddy, xz, xyz. Okay, so we can calculate it like I times, if you calculate this determinant, dy or minus y squared minus ddz xyz, this one, so you get negative 2y minus xy. Okay, so negative 2y minus xy, negative z times, this one must be ddx minus y squared plus, negative ddz xz. So it must be negative x, like that, and plus k times this one must be ddx xyz minus ddy xt. So it must be yz. Okay. So you can say that it is minus 2y xy comma x comma yz. It is the curve of f. Okay. As you can see, the result of curve is a vector, and divergence of f must be scalar. So it's a very different concept. So they are curve and divergence. And the last thing is the Laplacian. So if f is defined like this one, it is real valid function, but it can be defined on the multivariable. Okay, so in this case, we can calculate the Laplacian of f, and Laplacian f is defined like a divergence of a gradient f. But as you can see, calculation is very simple, as the summation of the second derivatives of all partial derivatives. So let's calculate the gradient f here. To do this, it was the summation of all partial derivative I equal to 1 to n, but n is the number of these numbers, so it is just a 3. So it means that fxx plus fyy plus fzz. Okay, so we want to find the second derivative here. So let's calculate the first derivative first. So fx is 3x squared yz plus yz squared. So if we take a partial derivative again, we get fxx. So it means that 6xyz, right? And let's calculate the fy here. Then it'll be x squared z plus yz squared. Sorry. It must be xz squared minus 2y. And fyy is, it'll be, okay, minus 2. Let's calculate the fz. You can see that it is x cubed y plus x 2xyz. And it'll be fzz is 2xy. Okay, so our Laplacian of f is just the summation of these second derivatives. So it'll be 6xyz minus 2 plus 2xy. This is the Laplacian of our given function f. Okay, so yes. There is some definition. If Laplacian of f must be 0, f is 0, then we say that f is a harmonic function. And if there is if a function f is called the potential function of f when the big F is the gradient f. In this case, we say that this function f is the potential function. Okay. Today I will stop here, and maybe next week we will talk about the more about car divergence, Laplace operator, and maybe there will be the parametric equations like that. And if possible, I will summarize the definitions in the lectures to prepare the midterm. Okay, I will stop here.